And also, it was observed by most of the physics community that Monte Carlo methods tend to work remarkably well in practice for these sign problem tree Hamiltonians. But then there were some indications of some difficulty of the problem. For example, in 2013, Hastings and Friedman showed some topological obstructions to path integral Monte Carlo methods, which is one of the most popular quantum Monte Carlo algorithms. And a few years later, Jarrett, Jordan, and Lecky, 2016, showed that diffusion Monte Carlo can be also sensitive to L1 versus L2 differences in the ground state, meaning that if we look at the same ground state, which now has like say all non-negative entries, then if we look at this ground state on through an L1 glasses, maybe it has the wave distribution looks very different when we look at this through an L2 glass. So that actually makes this diffusion Monte Carlo method struggle. So I will explain a little bit how we exploit these caveats and combine them into a hardness result, which is our main result, is that there is a family of sparse stochastic Hamiltonians on n qubits with a straight adiabatic path. Straight adiabatic path meaning it's just a linear interpolation between two Hamiltonians. And this adiabatic path features a spectral gap, which is inverse polynomial in n, and simulating this evolution requires at least 2 to the 5th root n queries to be Hamiltonian entries classically. And well, actually, even like very weak notions of simulation failed, and I show you how we prove this, what is the actual problem that we reduce it to. But before that, let me mention that this is an oracle separation. So this sparse Hamiltonian that we work with is given as an oracle, with a adjacency list oracle, or it's just a sparse Hamiltonian oracle. And well, if you want to prove such a big separation, then we need to rely on some oracle method or some hardness assumption that. So this is basically something that we can hope for, but obviously it's very difficult to prove like superlinear lower bounds in classical computer science without assumptions. So we prove this result by just showing that the following problem is difficult. So the Hamiltonians that we work with actually come from the adjacency matrix of a large graph, a sparse graph. And so the hardness result underlying this is about a graph problem. So if we are given via black box access sparse graph on 2 to the n vertices and the specific entrance vertex, then we show that we can find the exit vertex in polynomial time via adiabatic evolution of the corresponding Hamiltonian, which has a polynomial spectral gap and no sign problem because it comes from the adjacency matrix of an unweighted graph. And at the same time, any classical randomized algorithm must make at least 2 to the 5th root n queries to the graph, i.e. to the black box, for finding the exit vertex. So we have a complicated graph and we give an entrance vertex, and the adiabatic algorithm just very nicely finds the exit vertex. That's what I will show in the next slides. And then we also show that any classical algorithm that can find the exit vertex must take a very, very large number of queries to this adjacency list of this graph. And now I will explain the main ideas behind the construction. So for the purpose, I am first explaining the story from the viewpoint of the quantum algorithm. And from the viewpoint of the quantum algorithm, this will be just a path of length L. It's a super easy graph, very, very easy to analyze. And I will say that the entrance vertex will be just the first vertex and the exit vertex will be the last vertex. And the Hamiltonian is just the adjacency matrix of this graph. And the initial Hamiltonian will be just a Hamiltonian for which the entrance vertex has energy -1 and everything has energy 0. And the adiabatic path will be just an interpolation between the initial Hamiltonian and the Hamiltonian for this path graph, just a linear interpolation this way. Yes. And if I would like to just graphically represent this adiabatic path, then this is how the Hamiltonian for a parameter S is interpolated between the two Hamiltonians. And so one thing that some people might want nicer version is that here for the ultimate ground state, the ground state, the ultimate Hamiltonian, the ground state will be just some superposition over these vertices. And this is not a diagonal Hamiltonian, but we can actually get a version of our theorem where we just add one more interpolation between a final Hamiltonian, which will just give energy -1 to the exit vertex, and then this like two-segment path will actually exactly map the initial ground state, which is the entrance vertex, to the exit vertex. So here we even satisfy that the ultimate Hamiltonian is diagonal in the computational basis and finds the exit vertex. But the other draw is that it's not a straight path; it's like a combination of two straight paths. But both cases work in our proof. All right. So now I would like to explain how this simple-looking graph can be made more complicated gradually, in a way that the quantum algorithm still essentially says the initial path graph for the purposes of the adiabatic algorithm. So as a first step, we apply something that we call obfuscation. So each vertex of this length L path, we just replace by a cluster of vertices, except the entrance and exit vertices, which remain a single vertex. And we do it in such a way that we build a large uniform tree on the first few vertices around the entrance vertex. And it will say every vertex will have a m² children here, some number of children. And we also do the same thing around the exit vertex, and we call these parts of the graphs funnel. And once we stop for a fixed depth, we stop this construction. And from then on, all the clusters will contain the same number of vertices, a constant number of vertices, and there we will just add the random matchings between these clusters. That will be the edges between these middle clusters in the tunnel section, and there we add, well, m edges, m independent random matchings between the clusters. And if we view this graph in the symmetric subspace, which is spanned by uniform superpositions over these clusters, then we just get back the path graph. The Hamiltonian in this subspace was just the Hamiltonian of the path graph, except the edge weights will be m between the nodes, but that's just a constant scalar factor. So in the symmetric subspace, everything looks like it looked in the path graph scenario. But if we look outside of this symmetric subspace, then there might be other states that have very low energy. So what I didn't talk about, how we can preserve the gap property of this Hamiltonian. Maybe this Hamiltonian would have no very small, exponentially small spectral gap. And we take care of that by adding a uniform degree m expander graph, degree 2m. Well, so like something linear in m expander graph on every cluster. And again, this will be just a random uniform regular expander graph. And well, what it will do, it will essentially represent the self loop of all of these uniform on this path graph, which doesn't change again the energy landscape, but makes sure that everything which is outside of this symmetric subspace has much larger energy. And this is due to the property that this expander graph has this regular expander graph has the smallest energy state is the uniform superposition, and everything above this has like constant larger, proportionally constant larger energy. So it will be some omega m larger energy. So we can really just focus for the purposes of this adiabatic algorithm and also analyzing the gap in this symmetric subspace. And then there is another step, which is the decoration. And here we just add the fixed number of trees to every vertex in the graph, which is now in purple edges here. And these trees will have roughly m children at every level, or at most m children at every level. And at most m of these trees are attached to every vertex. And this just makes sure that actually one can analyze and one can see that all these new graphs attached together form a forest, and this forest has a small spectral norm. Therefore, this is compared to the gap that we already have, and this will be just a minor perturbation to the spectrum, and therefore it will not really affect the adiabatic algorithm or the spectral gap again. I will tell you a little bit more about this in a few slides. And now I just want to explain why these modifications make the life of classical algorithms much harder. And so basically in this
Sorry, Andras?
Yes?
Can I ask a question?
Sure.
Does the red edges form an approximate projector onto the symmetric subspace?
Well, you can think about that way indeed. It's not a projector because maybe the highest energy is like the highest eigenvalue has eigenvalue m, and the second highest say m/2, and then there are a bunch of states that have like energy or an eigenvalue between 0 and or like I don't know, minus m/2 to m/2. It can be like a full rank matrix, but yeah, the highest energy is indeed proportional to m. It is just m, and that is corresponding to uniform superposition. So it's not a projector itself, but something which is, approximating in some constant distance the projector. Did that answer your question?
Yeah, I think so. Thanks.
Maybe just to clarify for myself, so the points that you made so far was that the graph with all the decorations, this has a constant normalized spectral gap, and this is the only thing that you care about for the adiabatic algorithm to work out?
Regarding the clusters, regarding the clusters, yeah, we add these expander graphs to really like mark this this symmetric subspace as the subspace which contains the lowest energy states, and everything above that is like much higher energy. So I can just analyze the gap within this symmetric subspace. Okay. So now a word about like why these modifications that don't make much difference for the adiabatic algorithm, why are they so difficult for a classical algorithm to track? And well, the obfuscation step, we can think about it as this is one that is tricking path integral Monte Carlo with all these random matchings between the clusters and all these expander graphs attached, random expander graphs. We just have a huge number of very, very long cycles. And basically these long cycles that are hard to find or detect or deal with classically, that is in some way this topological abstraction that Matt Hastings and Michael Friedman they found. So basically this is like a computer science version of the topological abstraction that appears here, and this is due to this a huge number of very strange looking long cycles that are hard to deal with. And the second step, the decoration, we can think about this as something which tricks diffusion Monte Carlo algorithms, because from the L1 perspective, it throws away a lot of the weight of the ground state, but these amplitudes that are put into the leaves of these three graphs, they are very much uniformly distributed, very tiny amplitudes, but many of them, and in an L1 sense they matter, and they just attract most of the way of the ground state, but in an L2 sense, then things are very differently, they don't matter at all. Okay, so a little bit more explanation about this decoration.
So Andreas, can I have a question?
Yes.
So the obfuscation step that doesn't trick diffusion Monte Carlo, is that correct?
Yeah. In fact, once you are here, you can just do a random walk. Just do a random walk on this graph, and it probably, like, I don't know, half you, probably the 1/4 you step left, probably 1/4 you step right, probably half you stay along, but eventually you'll get through this tunnel. Once you get through the tunnel, you get to this funnel, and then you understand the structure and can easily go to the exit vertex. So it's very simple random walk, just works on this graph classically.
Okay, thanks.
And that random walk is like some baby version of the diffusion Monte Carlo, say. Yeah. So now a word on why this decoration step, where we attach a lot of camouflage or decoration trees to a vertex, why that does not affect the adiabatic algorithm too much. And as I told, each attached tree has a degree bound of order m. And one can see that the forest, where every vertex has a degree at most m, it has spectral norm at most order square root m. This is because this graph is very much expanding and lots of leaves. It's a back on the envelope calculation that the corresponding edges and symmetrics has order square root m norm, spectral norm. And well, the spectral gap of the adiabatic path just for length L path is 1/length square. But here, due to the structure of the graph, we basically had m times the edges and symmetrics of this original path graph. So the spectral gap after obfuscation step is m/L square. And the perturbation that we do with the decoration is order square root m. So if this order square root m perturbation is much smaller than the gap m/L square that we have, or in other words, if square root m is much larger than L squared, then the spectral gap cannot close under such a perturbation. And as a consequence, the ground state suffers only a minor perturbation in L2 norm. And therefore, the adiabatic algorithm is not suffering from this, and the gap doesn't close. However, if the trees are polynomially deep, then the L1 weight of the ground state moves onto the attached trees. And that will make a huge discrepancy between the L1 and L2 weight versions of the ground states. Because yeah, in L1 sense, most of the way is on these newly attached trees, whereas in L2 sense, the ground state barely changed, so most of the weight is on the original graph. And so now I explain why this decoration is really crucial for showing the hardness result that we have. And well, as I already answered these two. Oh yeah, so Anurag asked the question, what if I just have the obfuscated graph? I can just do a simple random walk and then I can find the exit vertex in polynomial time. Now I attached a bunch of trees and say these trees have uniform always the same number of children up to some depth t. Well, if I would have just such a simple decoration, then we can effectively filter out these attached graphs. And then after we manage to filter out these newly added 3 graphs, we can just go back to the same random walk on the original obfuscated graph. So that would be a problem. So how you filter out these newly attached trees is the following. After you traverse an edge in the graph, then you perform a non-backtracking trial walk. And if a leaf is found after these steps, then we know that the camouflage tree was entered, because the only leaves of this graph are just in the attached decoration trees. So with this, like after I do a step, I do a very simple check. And if the check says that I entered a tree, then I just backtrack and then I do another step, and I can make sure that I only walk on the original graph this way. And then the random walk algorithm works simply. And in order to prohibit such algorithms, we attach trees that have a fractal shape in the following sense, that the trees are designed in such a way that the expected hitting time of a leaf barely changes while we are moving deeper into a tree, making these camouflage trees hard to recognize. So in the case when we attach trees of the same depth, then if we are doing one step down on this tree, then the expected hitting time, which is it changes like by 1 on the of a non-backtracking random walk. So it's very easy to like realize that we entered a camouflage tree, because as we go deeper into it, somehow some random walk algorithm starts to behave very differently than it behaved before, and we can just detect this change and then thereby filter out the trees. However, if we attach trees that have a fractal shape, then this expected hitting time of leaves barely changes, and we just design it such a way. And so this construction is actually the idea that comes from Matt Hastings, how to make this classically hard. And once we have these attached trees, due to the fractal shape, due to the random labeling of vertices, no classical algorithm can navigate through the decorated graph, and therefore any classical algorithm will get lost spending an exponential amount of time in these camouflage trees before finding the exit vertex. And that's the main idea behind our hardness proof. Yes. So here may be a word that, yeah, this fractal shape, this idea is really from Hastings to how to construct these fractal shape trees that have this property. And we just made some modification to this construction, where somehow how many levels are there as approximate like self-similarity of the fractals. It was quasi-polynomial in Hastings construction, and we could make it like this sub-exponential. That's one of the technical contributions. And I wanted to say a few words about how this result compares to the glue trees problem of Childs et al. And well, this is basically their construction. There is also an entrance vertex and an exit vertex. There is 2 binary trees growing out of these 2 vertices, and in the middle layer there is basically two random matchings between these layers, or one long cycle, something like that. And again, this algorithm reduces to a path picture by taking the cluster vertices as like cluster states, which are uniform superpositions over things that are a fixed depth from the entrance or exit in this graph. And then it's just a path graph, and you can analyze it that way. So that's where the quantum algorithm gets the advantage. And so the similarities between the 2 constructions that we have and this validated trees construction is that neither Hamiltonians have a sign problem, because they just come from adjacency matrix of an unweighted graph. And the quantum advantage stems from staying in a symmetric subspace. And in both cases, a quantum walk can efficiently find the exit vertex, even the entrance. Now the difference is that in the valid trees problem, the glue trees are three regular and have an exponentially small spectral gap. And actually, the hardness proof comes from the fact that it's a regular graph. That's very crucial to it. Whereas our graph, but unfortunately, this regular nature of the graph makes this spectral gap basically exponentially small, and there doesn't seem to be an easy way around it. So in our case, we want a large spectral gap, and therefore we have a non-regular graph. But then the classical hardness needs to come from somewhere else than the regularity of the entire graph. And this comes, in this case, from the fractal shaped trees that Hastings introduced. And finally, I would like to close with some open questions. So one open question is that the original construction of Hastings actually utilized an adiabatic method for sign problem-free ground state energy estimation. So the method is sign problem-free and adiabatic, and it can estimate the energy of sign problem-free Hamiltonians. And this is an interesting technique itself, and maybe it could find this construction could find applications in proving further results. But we don't use this subroutine in our newer version. And well, of course, it would be very interesting to find sign problem-free Hamiltonians of practical interest that would provide such a large speedup. And another question is whether sign problem-free Hamiltonians are at least marginally easier in general. Like, is there a general simulation algorithm that works in time barely sub-exponential, or just something like square root 2 to the n? We don't know the answer to that yet. Maybe you can still exploit the lack of signs in a way that gives you advantage to brute force methods. But well, it cannot give you too big advantage, but maybe some advantage. And finally, I think the main open question that remains is that what is the classical complexity of simulating adiabatic evolution for frustrated local Hamiltonians with no sign problem? So if we have a local Hamiltonian which is frustration free, then Bravi and Tehal show that it's classically simulable. If it's a non-local Hamiltonian, just a sparse Hamiltonian, then it's very hard to simulate classically, as we showed in this Oracle model. And in between is frustrated but local Hamiltonians. And some recent results by Bringwatt and Jarrett from 2020 suggest that in order to prove hardness for this, one would need to use a different kind of ideas, different hardness, not stemming from these symmetric subspaces, because that's likely that you can classically simulate when the hardness would only come from symmetric subspaces. And yeah, this is so if you have any more questions, then please ask them.
Okay, thanks a lot, Andras. I'm clapping on behalf of everyone who can't do it. So thanks a lot for the talk. I think we have at least one question. So anyone can speak up or ask their questions in the Q&A. I see there's one in the Q&A. Anurag, I don't know if you want to pick it up.
Yeah. So Eddie asks, is it possible to construct a regular funnel, regular tunnel? And if not, then why not?
Well, the tunnel itself is kind of regular. So the way that we attach these trees is such that if you are just in the tunnel or entering these trees, then initially this graph just looks uniform. It only starts looking non-uniform when you are going deeper in these trees, or like some section of these trees, or if you are in the funnel parts. And well, if you would have a regular graph, then the regular graph would have the ground state, which would be just the uniform superposition over all the vertices. And the problem then it has exponentially small overlap, in particular with any vertex, entrance vertex or exit vertex. And this makes it difficult to construct an adiabatic path which wouldn't have an exponentially small spectral gap. I hope it answered the question. I'm not sure if it was answering it.
Maybe we'll let Eddie. Wait, I don't know if Eddie is on the.
Other questions?
So one question I have is, why does the regularity imply that the spectral gap is very small? I think you just said something about it. Don't follow.
Yeah. So if you have a if you have a regular graph, then the adjacency matrix will be proportional to a stochastic matrix, right? So in particular, the principal eigenvalue, the Perron eigenvector will be just a uniform superposition over all the vertices. And so if you are doing an adiabatic path through such a construction, then you would initially start with a state which is like, say, concentrated on the entrance vertex, and somewhere in the middle of the path where you would have just the adjacency matrix of this graph, it would have just the uniform superposition as the ground state. And these two states have exponentially small overlap. So unless you somehow have more structural understanding, it seems unlikely that you can find a path which doesn't have exponentially small overlap and interpolates between these two states. At least we don't know how to do it, for example, in the welded trees construction, and yeah, it just seems very hard in general. So that's the intuitive reason why I say that using a regular graph would lead to an adiabatic path which has exponentially small gap.
Great, thanks.
So by the way, Andras, you said a few times, so this construction is randomized? So
yes.
There's a, so can you de-randomize the construction? So so you use randomness for the expanders, which probably doesn't matter. And then for placing these trees, and maybe some other things.
Yeah, so actually, yeah, the fractal shaped trees, those are actually all the same. So every tree that we attach is just a copy of a fixed fractal shaped tree, say. So the trees are not randomized, that's a fixed construction. And I agree that that for these like expander graphs on the clusters, that's not very crucial that they are random probably. That probably doesn't matter too much. But we seem to rely on the fact that these matchings between the clusters, they are random. Like you don't have any structural understanding there, and that we use in the proof. It's a good question whether we could just get around it. And is your question like, say that the graph would have a fixed structure and you would only randomize the labels of the graph? That would be like a de-randomized construction?
No, a de-randomized construction would be a completely de-randomized construction. So just maybe for each n you could get a single graph, or maybe for each n you have a family of graphs that comes with an algorithm that, but let's say a polynomial size, a family of graphs that's explicitly constructed.
For each, sorry, I didn't understand what you said. For each end, you said there is a fixed graph.
Yeah, so yeah. So for each n, for each integer n, you'd have a graph, you know.
Oh yeah.
Together with an efficient algorithm that generates these graphs as a function of n.
But then you would even keep the labels fixed. So
no, right. Okay, so let's say you just randomize the labels. So you can't keep the labels fixed, right?
Yeah, that I mean that yeah, then you know the
Or
label.
at least, I don't know, at least the exit needs to be random.
Yeah.
I guess their labels seem like well, I mean, I don't know if this really matters from the point of view of showing separations or algorithms. I was just curious if there was some if you felt that there is some essential use of very high degrees of randomness, or if you can say, well, here are the kind of properties. So for example, for the expander, it's clear what kind of property you're using. And so what you're saying is that for the bipartite graph, it's maybe less clear.
Yeah, I think we mostly use the fact that these matchings are random between the clusters. That's the other sources of randomness are less important. And yeah, I could imagine that maybe you could de-randomize in a way that it's only a few graphs that you can consider, but the labels are random. But we didn't think much about this.
So then you'd have okay, never mind. Sorry, it's okay. Okay, so we have a couple more minutes for questions. If there's some other questions.
So this question by Chinmay in the chat. If you can de-randomize, can you remove the oracle from the separation result? I think it's follow up to the same discussion we just had.
Yeah, that's what made me hesitate. But I think okay, maybe Andras can answer it. I mean, I think the random oracle is still used for the labels. So you have there, you just have a purely just a random oracle for that.
Yeah, that's a good point.
And indeed,
yeah.
you need a random oracle, otherwise you'd. Okay, so maybe we'll end right on time. And thanks, Andras, again for his talk. So thanks a lot, Andras.